Hello everyone. In this video, we're going to discuss the paper by researchers from the University of North Carolina, Chapel Hill. The main idea of the paper is to combine mixture of experts or modular deep learning with standard gradient-based training instead of non-differentiable discrete routing that use gradient estimation techniques. The authors avoid discrete routing by using a single merged expert obtained by weight averaging all expert parameters. This allows routing through a single expert, which does not significantly increase computation cost. The paper demonstrates that this approach outperforms methods that use discrete routing, whether fixed using metadata or learned using gradient estimation. The figure illustrates the contrast between discrete routing and the proposed smear method. In discrete routing, experts are organized into blocks, which are placed as intermediate layers in the network. For each block, a router makes a decision choosing to route the input or hidden state representation to an expert from the different experts in the block. Typically, this requires the use of gradient estimation to learn the routing decision, but can also use fixed routing decisions that do not involve training the router. These methods vary in how they make the routing decision and how they construct the output. In this paper, 3 discrete routing-based models are used as baselines, namely straight-through Gumbel softmax, reinforce, and top-K. We'll go over these briefly. In general, for mixture of expert routing, the router is often lightweight network applied to an intermediate hidden state in the model. The output of the lightweight routing network parameterizes a discrete probability distribution over all experts. In straight-through Gumbel softmax, the Gumbel softmax distribution is used as a substitute for the categorical distribution learned by the router. This is done since the Gumbel softmax distribution is smooth and thus permits gradient-based training. Here, the differentiable variable is used only for the backward pass. The categorical distribution is used for the forward passes and during inference. In the method reinforce, reinforcement learning is used to estimate gradients. Because of the high variance in the reinforce estimator, the authors use a baseline that is generated by a small neural network with a single hidden layer that takes as input the hidden state and is trained with a Huber loss. The overall loss function is the sum of the policy gradient, policy entropy, and value loss. In top K routing, the router sends the input through the K experts that are assigned the highest probability. Here, the estimator selects the K subnetworks with the highest probabilities, and the output is a weighted sum of all the subnetwork outputs, each weighted by its corresponding routing probability. In addition to learn discrete routing via gradient estimation, the authors look at 3 baselines that use fixed routing via heuristics or metadata, namely tag and hash routing and single expert routing. In tag routing, a hand-designed heuristic routing strategy based on prior knowledge about the data is used. If we know the task or domain of each example or data point, we designate an expert for each domain or task and match examples to routers with the same tag. In hash routing, a fixed hashing function is used to determine which expert to use for a given example. This approach does not route similar examples together to achieve specialization of experts. Finally, single expert is the simplest method, which, as the name implies, uses a single expert. Routing in this case is trivial, as all examples go through the same expert. For this baseline, the authors use 2 models, one that matches other models for evaluation, either by using a single expert with n times the number of parameters used in models with n experts, or by using the same number of parameters but with n times the compute as a single expert. The authors use 2 other learned routing methods. Atomix uses a random non-adaptive routing strategy and adds a consistency loss to encourage activated experts to share information and to discourage their divergence. During inference, the parameters of all experts are averaged together to form a single expert. In this case, no adaptive routing is used. Another baseline is latent skills. Here, the task for each example is known and a task skill matrix is learned that specifies which experts are activated for a given task. This binary task skill matrix is learned also via the Gumbel sigmoid trick. For inference, the parameters of the different experts are weighted based on their corresponding weights in the task skill matrix, and then averaged to create a single expert used for inference on an example from a particular task. Finally, the authors include another baseline that employs gradient-based soft-merging, which is ensemble routing. Here, the input is passed through every expert, and the output is computed as an average of the expert's outputs weighted according to the router's distribution. This method is like the proposed method smear in that the gradient can be computed, but unlike smear, the computational cost increase for ensemble soft merging is significant. Finally, In SMEAR, which is shown on the right figure, a given router's distribution is used to average the parameters of the experts, and the input is routed through a single merged expert. The advantages of this method is superior performance over discrete routing and that it can be trained with standard backpropagation without incurring significant computational costs. This figure shows the results as the average accuracy versus inference speed in examples processed per second for models using different routing approaches on different NLP tasks shown on the left and on computer vision tasks shown on the right. 8 datasets from the GLUE Natural Language Understanding benchmark are used for evaluation. The base or backbone model for these experiments is a pre-trained T5 model. Blocks of experts are added after modules for each transformer layer in both encoder and decoder. 8 experts are added for each block, 1 per dataset. This gives a total of 60 experts. Training is done by freezing pre-trained parameters and tuning expert parameters. For computer vision, a ResNet 18 pre-trained on ImageNet is adapted to datasets in DomainNet, which consists of multiple object recognition datasets from 6 domains. Here, each domain is treated as a tag, and so for each expert block, 6 experts are introduced. Similar to the NLP experiments, pre-trained parameters are frozen and expert parameters are tuned during training. Fixed or heuristic-based routing methods are shown in blue, while gradient estimation methods are shown in cyan. Methods that do not perform adaptation learning, which are single expert and ADA mix, are shown in purple. Hash routing performance is significantly below other methods and is not included in the figures. We see that for both NLP and computer vision, SMEAR has the top performance among methods that have high inference speed. The ensemble method has the top performance overall, but only at the expense of inference speed. A breakdown of the results by dataset is also included in the paper and shows that for certain datasets or domains, other methods outperform SMEAR. But as we can see on average, SMEAR performance is competitive given its speed. We also note the reason why some of the methods shown are faster than SMEAR. To see that, consider the cost of merging the model parameters. Even though the input is not passed through every expert, like ensemble, which is the slowest method, and even though its gradient-based approach is more efficient than gradient estimation methods, it's still slower than no adaptation methods because its adaptation scheme involves averaging expert parameters. As we can see, the fastest methods use no adaptation but perform worse than SMEAR. Thus, SMEAR is presented as a method with a competitive performance-speed trade-off. The idea behind this figure is to qualitatively analyze the specialization of experts. In the NLP case shown on the left, or subfigure A, we had 8 datasets and 8 experts, so we see each matrix as 8 by 8 with datasets in rows and experts in columns. The values in a matrix correspond to the distribution of a router, and here we see the routers from the feed-forward network in decoder number 3 and the feed-forward network in decoder number 5. The values are obtained by averaging the distributions of all examples in a given dataset or domain. Similarly, on the right, we see the analysis for the computer vision experiments showing routers from residual layers 1 and 5. Looking more closely at the routers from T5 GLUE, we see that the first router largely assigns an expert to examples from each dataset, while the second router mainly routes all examples to expert number 5, with the exception of some datasets that are designated a distinct specialized router. We see STSB examples are mainly assigned to router 8, and SST2 examples are routed to expert 1 with a 100% probability. We can also tell from the figures that overall, routers exhibit a high degree of specialization in the T5 GLUE NLP model, whereas we see less specialization in the computer vision model. This concludes our discussion of the paper. Thank you for watching.